Welcome all today. I'm very happy to see so many participants for these final presentations. The attention it gets is great. And I believe that we have some very interesting results to share with you guys. So I'm very happy everyone is here tonight for the AI for Wildlife Challenge, the second one, where we will be working towards creating a machine learning model for on-edge detection of poachers. We are very proud to present this tonight to you guys because 2 months ago, we started off by finding a lot of AI enthusiasts and developers to build a team to tackle this challenge. And a lot of great people came out, and we built an awesome team to work towards this goal together. Eventually, we had 5 teams who will all be presenting their results today. So what we're going to do is we're going to first head into an introduction of Spots. Peter, CEO of and co-founder of Spots, is here today to tell us something about the mission that they're onto, which will be followed by the final presentations. We have the data wrangling group today, the model exploration, we have RGB data, hardware team, and an autonomous flight team. We're very excited about this, and there will be some closing words from our own Buster and Robbie from Spots, who will be thanking everyone. So I'd like to give the word to Peter.
Oh, well, cool. I mean, it's probably not mine to do, but I'd also just really like to welcome everyone to the discussion this evening. I guess that if we needed any confirmation or any justification for what we're all trying to do, I think the results and the outcome of the COP26 discussions and meetings in Belfast, which we concluded on Friday, would give us that. And certainly, I'm not going to be trying to. Not my intention to detract from various people's efforts. But let me put it this way: okay, if COP or the UN coordinated efforts, we're going to put together an initiative like what we're discussing tonight, Fruit Punch AI, the challenge. It would have taken them millions of dollars in a couple of years. That's a fact. So, the small, nimble operations, the brains trust that really care, the people that commit themselves to this kind of initiative, that is really what conservation endeavor needs worldwide. And we need it probably more down here in the southern tip of Africa than most others. The assault on our wildlife resources is massive. It's from virtually any species of animal, insect, reptiles, plants, you name it. And I think without the initiatives and the concerted efforts of people like us sitting around these phones tonight and screens, the wildlife species, the fragile wildlife resources of this world don't stand a chance. We will simply not win. Robbie and I started Spots 15, 20 years ago, I guess. We fought a battle against and fought in wildlife protection with essentially only boots on the ground. And it took someone like Buster to come along and excite us about the potential for AI, for IT in very many aspects, to play a major role in conservation. We already had a drone development, or let's rather call it an unmanned aerial vehicle development going, driven by my partner, Robbie. So, we kind of had a platform that we could use, but the smarts and the intelligence that goes into development of AI, we simply didn't have. And it took Buster's initiative. You know, he's a dynamic guy. For us to meet with him was an absolute pleasure. And that's kind of the whole background to the formation of spots. We were never ever intending to be species specific, and we certainly still aren't to this day. So, you know, to each and every one of you out there, whether you've given 5 minutes, whether you've given 5 days, or 5 weeks, or 5 months, please know that your contribution to conservation effort is it is honestly needed, and it is deeply, deeply appreciated. And it's perhaps easy for Rob and I, you know, because we get to see some of the heartbreaking parts of poaching, but you know, we also get to see some of the beauty of what we do. And I deeply respect the fact that there are many people who've made a contribution to this effort who don't get to see that, who don't get to enjoy either the good or the bad. But you know, so for us, potentially, it's probably easier. You know, for us to see a rhino calf toddling along with its mother, you guys don't get to see that, and pangolins scurrying around. But please know that tonight when you go to sleep, your efforts are making a huge difference. We would hope they make a huge difference for a long time to come. And then all of you, we don't have unlimited resource, but know that you have a home down here in the southern tip of Africa. Anytime, you'd be more than welcome to come and see the animals, come and work with us, come and see how it all works. You'd be always very, very welcome. So our sincere thanks to all of you. Again, from this little southern tip in Africa, with all the species that we're fighting to protect.
I think we lost Peter here for a second.
Real cliffhanger.
Yeah.
I have some time for the goosebumps on my arms to calm down again.
He's a very inspirational speaker. I feel already very appreciated for the challenge, and we have all the presentations yet to come. But yeah, unless we're getting Peter back right now, I think it's a good moment to start off with some of the presentations to actually see what these challenges have brought us. Yeah. So if you're going to watch the recording, Peter, thanks a lot for the introduction. It was very nice to hear those kind words. And then I'd like to give the floor to the first group presenting tonight, which will be the data wrangling group.
Thanks, Dorian, for the floor. I'll be presenting on behalf of the data wrangling group. And I'll share my screen real quick. And we, as the data wrangling team, is responsible for pre-processing the data before it is being modeled. So whenever you want to train a detection model, such as the object detection model, which can see poachers, you first want to have the data ready for these models, such as you can train. The computer can see where these poachers are, and then it can hopefully recognize them in the future. So we are kind of we're assigned to do a little bit of the boring part, and then other teams can experiment with exciting models and see whether or not we can actually detect these poachers or humans on the images. So this is a quick introduction of the team. You can look at it for yourselves. Hopefully they're all attending right now. And so the first goal that we set ourselves was to deliver additional training data, because in the first challenge, the data was already pre-processed in a nice manner. So we thought that we could contribute the most if we can deliver more data, so that the models can train, have seen more examples of humans in wildlife. And so that we went to look for new data sets and make these homogeneous. And with homogeneous, we mean that they're all stored in the same format so that the models used can all use the same data sets. And to extend the data even more, we wanted to introduce data augmentation. Now, the other steps we also want to do is just for convenience, want to track who uses the data sets and create a loader for each data set so that this method is standardized. We set out to find these new data sets, and we already had the data sets which someone found in the first challenge, which is the Aachen data set. It contains 1,700 images with humans and cars. And we also found an additional data set, which is actually a lot bigger, with 62,000 images with 14,000 humans, but also images with animals. And we set out to convert these data sets into the same format as the data that was already being used in object detection. And what is meant for the Aachen data set is that the first thing what we wanted to solve is these black borders around the edges. We thought that it could be maybe a problem for the models, so we wanted to remove these. It was a little bit tricky, but we ended up succeeding, and this way you can see from the first image to the second one, these black borders are now removed, which hopefully helps the models. And here at the top right, you can see an example of how this data set looks like. So we have some cars which are annotated in red, with some humans which are annotated in the green bounding boxes. And then we also had the LIDA data set. This data set was actually fairly good, fairly clean. However, in this data set, the humans were colored in white, which is the opposite of the other data sets. So the main thing that we did is change these images, reverse the colors of the images such that black is now hot, and then the people are also represented in black. And of course, the format behind these annotations was also different. So we translated this into the same format. And now these should be ready to be used by the object detection models. So we have these three data sets, which then can now be used. However, the structure of the folders is still a little bit different for each of these data sets, and the images have different sizes of width and height still. So what we want to achieve is to standardize loading of the data sets in a loader for each of the data sets, and from this data loader, the object detection model can use the datasets from one single point. And because sometimes it happens that there's a bug or something has to be changed, and then we wanted to track who is using which datasets, so that if a bug is fixed or found, then everybody that uses the dataset can be notified. Because if you don't do that, then you change something, and then if the one using it doesn't know it, then he might run into trouble as well later. So I had a quick demo of the data loader that we created. So this is actually a notebook, and the first thing that we applied was downloading the required data. So from here, if you run this cell, you automatically download the data set that you need and the annotations for this data set. Now you can, I won't bore you with all the details, but now here we have a dataset class, which represents the dataset in the PyTorch manner. And if we scroll down even further, here we have some examples. So here, if we have a batch of data, we can run this cell, and then it shows the first image of this next batch. And this way, we have done this for the Aachen dataset, but also for the AFO Wildlife 1 challenge dataset, and also for the LIDA dataset. And from there, we hope that this dataset class that we have created can be used by one single model, and to avoid confusion in the future. So for the future of actually the data wrangling team, if we were to continue the part that we've done, was to apply these data sets to the object detection model to see whether they have a positive hopefully positive effect. And if not, then what kind of works needs to be done to change to make it a positive effect. Also to create a standardized method of labeling and loading new data. So now we have for the 3 data sets that we have made homogeneous, but also a lot of other teams, and there's still new data coming in. So it would be nice to have a standard method, but also what we aim to achieve is to kind of make a tutorial from our data loader, such that people that are going to use it in the future have a very easy time getting into the challenge. And what also would be, we think that would be very useful is to perform some data analysis, such that it becomes clear. So data analysis for each of the data sets, so it becomes clear what each data set contains, and from there different new decisions can be made. So that was it for the data running team. Hopefully it was all clear, and hopefully it's a useful contribution to the team. Thank you.
Thank you, Jeroen. I'm sure it will be useful. And it's a really good idea indeed to make a tutorial or a little demo for future use of these of these classes you made. I think it's a really good outcome. And yeah, I'm looking already forward to see the tutorial as well.
All right.
So I will open the floor for questions if there are any. So feel free to ask all your questions in the chat or speak up if you like. And otherwise, if there are not any questions, then Jeroen. Oh, we have one.
Yeah, quickly. Jeroen, just to recap, and just to make sure I understand what you've done. Going forward, are you saying that if we want to start looking forward to creating a census AI database, it would be running through this, and this would label and strip everything apart and format it correctly so it can be processed faster, as opposed to what, doing it manually? Is that what you've done here?
No, actually, that's not what we've done. I have people been working on that for from other teams.
Okay.
But what we've done is added new data sets to the similar format, such that they can be used for training. What you're saying is that when you send out videos, right, that are annotated automatically. That's not what we have done, but I think some other teams have made steps in that progress. So.
Okay, great, thanks.
All right, I see one question about the cropping of the images. So how did you remove the black backgrounds?
So it was a little bit, we had 2 options. The first one is to basically detect the black backgrounds for each individual image, and then make a smart kind of cropping method. However, this was a little bit tricky, and what we've done now is there were 4 different types of dimensions in the data set, and for each of the dimensions we created a cutoff point, and we basically said, well, for if this image has this dimension, then we're cutting off such amount of pixels at the top and at the left, and just stuff like that. So we only manually tuned it for every dimension.
Thanks, Jeroen, for the presentation. And then I'd like to head on to the next group, and that will be the model exploration group.
All right, great. So I'm happy to give you this final presentation on our progress for model training and exploration. First, I would like to present the team that is still standing from all of the team members. There is Vasu. He was working on the classification model and did a lot of manual coding, which is really cool. We have Laurent, which was pushing us to meet all the requirements and specified some interesting things in terms of metrics and envisioned how all of this can come together to be deployed on the edge. Then we have me. I've been mostly focusing on the detection model. We have Adrian, who was our ML ops engineer, and he created a very cool machine learning pipeline that we will also see. And we have Wei Wei, who was helping us on pretty much all fronts and took a lot of responsibility on herself regarding data analysis and preparation and coordination with the data wrangling team. So our challenge was to deliver a performant poacher detection model that can run on the edge device, which is the most important point. And we basically continued from the challenge number 1, where a model was already selected, and the model was Detectron 2, which has great performance, really. But the problem was that it is insufficiently fast. It is, in fact, very slow, and it takes more than 10 seconds per frame to calculate. And according to the requirements that we've collected, we're looking at something like 4 frames per second. And additionally, we didn't have any real known performance metrics on how well the model is performing on the test sets from the previous challenge. So we did some research in Detectron 2 and also some other possible approaches. And besides that, we also split into 2 different approaches, where we have a super efficient image classification step and a less super efficient, but still efficient object detection step with 2 different purposes. So we explored both of them. And we also came up with a basic continuous integration, continuous deployment pipeline, and worked with the hardware group on the deployment front. So here are some requirements that we have collected, and basically we already presented them, but the most important one, I think, was that we are able to detect poachers with more than 70% certainty on some frames, and that speed should be about 4 frames per second, or ideally a bit more, and that we can track, or let's say continuously run these detection and classification models on device, so that we are able to monitor the situation while the drone is operating. So regarding our progress on challenge number 2, first we've collected our insights from challenge number 1 participants that told us a lot about the data and also the modeling that was done so far. Then we looked into data, so we did some data analysis there to see what exactly we're dealing with. And we were exploring multiple state-of-the-art detection and classification models, out of which we've selected a few that fit all the requirements. And we then proceeded to train those models and also had initial results based on which we came up with, I think, very important dataset observations, which we forwarded back to the data wrangling team, which led to the creation of an improved dataset. And also a completely new dataset for the classification model, which ended up being quite significant. The main issues that we were facing, however, were that the datasets were actually quite problematic. That's why we had to come up with those observations to fix them. And that the datasets were actually still non-representative of the real situation. So there was some talk about the drone and the stabilized camera and that it may change, etc., etc. And it is always better if you have a really representative data set there. And we also faced some issues with compute power and model deployment. The compute power front was basically because we didn't have all the necessary resources to really train powerful models. And there were some issues with model deployment because not all model architectures transition so easily on edge device. Then a couple of words on the MLOps pipeline, which you can see here. Basically, the job of this pipeline is to represent everything that will be happening in the system from when new data is available to on-edge deployment. And the idea is that once we have new data, we can easily trigger the process of training a model on Rescale, which we also set up. And this model is then evaluated, and we are logging these metrics, checking if the model performance has improved given the new data. If yes, then we update the model weights, and the model weights are pushed back to GitLab, which is our pipeline orchestrator. And this model, once improved, is sent to the hardware team, where it is converted for edge deployment and tested. And that is basically one life cycle, which repeats once data gets updated. And we have here some nerdy results of classification and detection models. So first, we chose custom VGGNet as our best performing classification model that reaches a really high accuracy in training and also really high accuracy in validation. But the test accuracy drops a bit on the test set. But as you will see on the video, this isn't really such a big problem. It still performs quite well. This test set, the problem with the test set is really that the video is from a completely different flight. So there is a huge flight difference and the terrain difference that isn't well presented in the training set. So we are quite hopeful that if we are able to unify this data between training and testing, we would actually be able to reach higher scores there. The benefit of the classification model, as you can also see here, that it's super fast to train. It just took 40 minutes to reach this amazing performance. And it also is very fast. As you can see here, it reached about 5 frames per second on the Jetson Nano CPU. So that's the non-converted version. And it's also very tiny. So only takes 3.5 megabytes, which is pretty much nothing in terms of deep modeling. For the detection model, as you can see, here we present mean average precision 0.5, which basically tries to measure in, let's say, roughly, don't use this as a scientific explanation or anything, that the bounding boxes from your ground truth and inference are approximately half covered. Let's put it that way. So here we have on training, again, quite a high performance, about 85 MAP, which drops a bit on the validation set and further drops on the test set, but this is still quite a good performance. As you can see here, it takes quite longer to train this model. And also for the future generation who might be watching this presentation, this model may not have converged completely. So if you would still continue training, it might even reach a better performance. And the inference time, as we found out, is about 6 frames per second on the Nano GPU, which is very good. And it is fitting the requirements. And the model size is also not too big in terms of deep learning models. Regarding the data set, here I have Aachen V2, but this is actually challenge 1 data set that has been cleaned up based on the observations that we've had. And it definitely improved the model performance here. And just to mention also the differences between the two and why we pursued the 2 different approaches. So for image classification, the main benefit is that it is super fast to annotate. Basically, you have to make a yes/no decision, is there poacher or not. The downside is that it doesn't give you location information within the image, but at least you know that if in the frame there is a poacher present. As opposed to object detection, which takes more time to annotate because you have to draw bounding boxes around everything, but it gives you a precise location within the image. And the second important thing here that I would like to emphasize is that for image classification, since it's such a small model and so speedy, you can actually use it in power efficient modes. So even if you're not covering a particularly interesting area with your drone, you can still run this model and it will give you feedback, is there a poacher or not, or let's say a human or not, while you can then turn to object detection once you're in an area of interest. For example, let's say that classification model is starting to give you a lot of yes, poacher present, then you start running object detection, which will draw more power, but it will also give you a precise location of where the poacher is present. So here we have some videos that show the results. On the left side, you can see the classification model. So here you can see a poacher. And when it's in the frame, it's saying detected. And once it's not, it's saying nothing. And simultaneously on the right side, you see also the detection model performance, which is circling the human where it is present. And one thing that you can observe right now here on the classification side is that there wasn't any false detections. While, let's go back a bit, you can see here that object detection still mistakes some objects for human, but do pay attention to the fact that the confidence here is much lower than once we come to the human, which is above 70. And I think you can clearly see the benefit of using both together as well, right? Because if you're using this one and it says that there is a detected human present, you can only run detection on those frames, and you will also achieve a higher accuracy plus get precision of localized human within the frame. But overall, I think that given the test set that we're dealing here with, the results from both models are quite good and could already help you figure out where the poachers are hanging out. So to finalize our presentation, we propose some next steps for either next challenges or some of that we can maybe even do after challenge concludes. So first of all, I would like to point out that building larger and representative data sets is probably the biggest improvement to these models that we could make. Because if you build larger data sets that represent different flight heights, different scenarios, different numbers of humans being present in frames, different objects like animals, cars, buildings, humans, you will learn to distinguish between them much better. And the second thing is to improve the training, validation, and test splits. As you saw that in training and validation, we had quite high accuracies, but on the test set it dropped because of the difference, of a huge difference between splits. So this can also be much improved. And especially once models are starting to be put in production, definitely go for cross-validation so that you're testing on multiple cuts of the sets. Also, one thing we didn't really experiment with is specific data augmentation during training. What we've used is for YOLO, for example, in the detection case, there is already augmentation built in, which works very well. But as you heard from the data wrangling team, they already provided some potentially better data augmentation techniques, which should be tried out. Then moving forward, definitely model hyperparameters needs to be tuned because we didn't really have much compute power and time to spend on hand tuning hyperparameters. So I think there could be at least a couple of % more squeezed out if we dedicate some time to hyperparameter tuning. And then we have to work on building out that MLOps pipeline, especially with attention to robustness, so that it is more robust when changes happen, and automation, so that we really achieve the whole cycle. And finally, once all of that is taken care of, we should combine both classification and detection into an application that can run on the drone, so that you will have an efficient poacher detection solution. And for the next challenges, what you can also do is already use the detection models that we've trained to simplify the labeling process. It may not work 100%, but at least it will label some of the poachers definitely for you, which will simplify a lot of the workload for larger data sets. For the curious, you can also take a look at our presentation here. We just linked some step-by-step guides, links, and interesting information for classification and object detection models. So if you have some time and are curious, you can take a look, and it will show you some interesting things there. Thank you for your attention.
Thanks a lot, Jaka, for your presentation. It's looking really good, especially those videos make it very visual. I think that's great. I would like to see if there are any questions.
Before someone raises their hand, I'll fill up some dead space here by saying that a really extraordinarily good presentation. Also, the visualization of the MLOps pipeline and all of that. It makes things really clear, and I think this is also like a great tool for other people in the community to learn about how these projects are actually tackled. So that's just really cool. So yeah, thank you for that.
Yeah, that's thanks to Adrian. He's quite good at it.
Amazing. Thank you, Adrian.
If you don't mind, I've got one question, but it pertains more, and congratulations. I think that's absolutely awesome. I'm sure Robbie would agree with me that the capability that you've developed there is already going to help us hugely. Okay. One question about the hardware. Do you believe that on the Nano we down the right route, or should we be looking at something else for on board on the Air Ranger UAV?
So I definitely think you're looking at the right hardware. Maybe just the timing is a bit off because of the chip shortage. It is really hard to get your hands on that hardware. But in terms of performance and the support from the community and the company that stands behind it to put models there and also use other tools that enable efficient inference on edge, I think it is definitely the right choice to go with.
Wonderful. Thank you.
All right, I see some questions in the chat about the color of the, if some data sets are colored in black as a pre-processing step, my understanding would be that humans would naturally appear white in a thermal infrared footage. Oh, see, Jeroen already answered this question.
I think his answer is correct. Yeah.
Cool. All right. If there are no further questions, thank you, Jaka. I believe you made a very good presentation and your team has done really well. So yeah, you can be proud.
I am proud of my team. Thanks.
Great.
Sorry, Jaka, just one other question. Okay, so the FLIR cameras, their thermal capability in daylight hours is also exceptionally good. The 70% hit rate that you're getting on poacher detection, would that apply as much after dark as it would during daylight hours, or do you see a difference occurring there?
So for that, I think best to listen to what RGB team has to say. But I do think that even in daytime, you can achieve the same performance, especially given the footage that I've seen, because most of the times you have quite a distinctive, let's say, scene where you can see objects that don't belong in the scenery. So I think definitely you can reach that performance. And the benefit, I think, will also be that daytime capture is easier to do because you can use, let's say, multiple devices because they won't be so expensive. So once you start scaling this up, if you have a fleet of drones capturing during daytime, you can quickly scale the data sets, which will give you higher accuracy for detection.
Hey, Jaco, my name is Noel. I would like to check and see with you, when you do the computing power of this information, would that be on board the drone or would that be at the base once it's transmitted that information from the drone to the base?
So the performance we reported, so 6 frames per second, would be on edge. And I think hardware team will have more to say about that, but they were able to convert these models and they were already running them on the Jetson Nano. So they will be the right team to explain more about the performance there.
Thank you. Waiting for the answer.
All right. Then let's head on to the next team. We have the RGB data exploration team.
Hello, everybody. Good afternoon for me, but could be good morning or good night for you. I'm from Team RGB. My name is Sam, and I'm a data scientist at KPI, which is one of the challenge partners. And let's jump straight in. So the team that did such an awesome job for Team RGB is Benjamin, who helped with training the object detection model and is doing his PhD in physics. Then there's me, who also did some of the object detection. Vincent, who again helped with model training and labeling. Samantha did labeling. Anna helped model training, labeling, and everything in between. And Aisha was comms and team coordination. So a really well-rounded team and made for a really fun challenge. So just to set the scene a bit, spots for the first time or for the first challenge are requiring poacher detection during the day because they're seeing an uptick in poacher activity. So ultimately spots wants 24-hour coverage. So they want to be able to detect poachers in the daytime using red, green, blue footage. So just, color imaging, and then switching to the thermal footage at night, which you just saw in the previous presentation. So that has been already thoroughly explored, but this was the first challenge where red, green, blue data was explored. So there was no data available at the start of the challenge, nor was there any modeling or previous teams' efforts to go off. So we were really shooting in the dark, and I think we did, again, a pretty amazing job. And the primary goal of the challenge was just to design a model for poacher detection in the day. So setting ourselves some objectives for the challenge. So we wanted to train a model capable of detecting poachers implement a flexible and efficient design system so that we could iterate with lots of different model architectures and different data sets that we were able to lay our hands on. And then at the end, we delivered a model checkpoint or endpoint to the hardware team so that they could run it on the on-edge compute device. So this is just an example of a raw image. So it's in 4K coming from the footage that we received, not actually from the drone that Spot is using. This is from a quadcopter, but it is as close as we could get to the real example. And as you can see, the people in the image are incredibly tiny. Like they're on this path here, but I'm pretty sure when I pulled up the image, you guys didn't even see them. So it is already quite a challenging task. So what we did was there's an image augmentation technique called tiling, which involves cutting this 4K frame into 60 or so subframes. And then that makes the subject in the image a lot bigger and a lot easier to localize for the object detector. So this was a really interesting augmentation step that we applied, and it ended up working really, really well. So the Spot's data was provided and used to train and test the model. So that was from the quadcopter. And it was a simulation of poachers walking through the nature reserve. Those were actually ranges that you saw in this in the example I showed. And then the direction of the camera angle was constantly changing. So I'll show you a little video now, but the quadcopter is a stationary flying drone. And it was also moved around to, I guess, try and simulate the drone flight, but it was quite challenging to use that data. And then obviously the nature of the landscape is that there's camouflage of trees, rocks, and vegetation and other things. So it makes for a really challenging and interesting problem. So I just want to show you an example of the video in 4K. It's really nice to watch. So this is just a quick snippet from one of the videos. So the quadcopter is really, really still. And the drone would typically be moving at a much higher velocity. But you can see that the poachers are walking, the simulated poachers, which is actually, they're in this call right now. So that's great. So just a bit more information on our data pre-processing. So we took the raw data given to us by Spot, which was in video format. The video is about 3 gigs large, cutting it into frames and sent it to Amazon's Mechanical Turk for labeling. It was really a seamless job. And then we processed the output from Mechanical Turk and then checked it and then sent it to our data loader. Then we trained our object detector and also our poacher classifier, which I'll explain now. So the data went into a training script, trained both models, and then the checkpoint was created and sent to the hardware team. So just an example of how inference worked. So the large 4K frame was cut into 60 smaller tiles or subframes. And then each tile was passed to a simple image classifier to classify whether the frame contained humans or not. And we got some really amazing performance there. And the idea was that the image classifier is cheap to run, but the object detector is very expensive. So if you pass the object detector as little frames as possible, you can increase your overall inference speed, which is really the point of this challenge. So accuracy is really secondary to how fast you can get the model to run. So then we passed those detected frames from the poacher classifier to the object detector and then localized those poachers in the frames. There we go. So just some results. For image classification, they have explained if detect a human or not. We used efficient net B0, which is a really great and fast model to train and also fast to infer. We fine-tuned it on the Spot's data and it was pre-trained on ImageNet. And then we got an average inference speed on a 4K image of 2.5 FPS. So that's without any quantization or model optimization. And obviously there's a lot of things you can do, one of which being to make the 4K image not 4K, like downscale the resolution before you send it to the model. And we just ran out of time there. But this is the speed you would get on Google Colab's hardware with a non-optimized model, which is really great. But even better is the AUC score we got, which is incredibly high. So the model was really, really good at differentiating between frames that contain poachers and frames that didn't. So even if you want to skip the object detection step, you would still have a really, really good idea of where the poachers were in the frame. And that is, again, extremely useful. You might not know how many, but you know, if you're really facing compute obstacles, then this is a really good segue to getting your result. Then obviously accuracy was incredibly high, and then just included the cross entropy loss at the bottom there. That's a training metric. So here are the object detection results from the models we tried. So we tried RetinaNet and Foster RCNN, and we decided to report the map scores for an IOU of between 0.5 and 0.95. Super technical, I know, but if you are interested, you can look it up after. The map is the standard for measuring object detection performance, and it's a really cool metric, and it's used for benchmarking all object detection algorithms. So it ended up that the RetinaNet was slightly superior. Well, I mean, it was actually very, very similar between the two models, but it inferred 1 frame faster per second. And the thing is that it's 11 FPS is so much higher than the previous 2.5 FPS, because these models only had to infer on about 3 or 4 400 by 400 subframes, whereas the image detector had to infer on a full image, or 60 subframes of the full image, which takes quite long. And then now I want to show you a demo of our end video pipeline. So I'm just going to start it again. So this is a video I showed you earlier, but now this is with the model running over the video. So again, the people are really small, but you can see now that the model is able to localize them pretty well. There are obviously some mistakes, and as the drone moves, it loses the people a little bit. But I think this is really great, a really great proof of concept for RGB detection of poachers in real life. So we are really, really pleased with this result. And I think that future challenges can have a really, really strong leg to stand on when they start. And then finally, we just have some next steps for the next team. So improving the annotation process. We found that using Mechanical Turk was great, but it was obviously very impersonal, because the service is just upload your data, do a few examples, and then send it out to the Mechanical Turk army of human labelers, and then they do their best, but often it wasn't good enough. So one such service is RoboFlow, but then Enlabeler is a South African service that does a really, really great job of labeling data in a way that is like with you and would do a way better job. So I would really recommend exploring other annotation options for the future teams. We would look to further optimize our models. So there's a couple of hyperparameters which we didn't have time to tune. So that has to do with the non-max suppression, and also just standard model parameters that could have had some tuning. And then we could have added an extra classifier to classify the whole frame before it was cut into subframes. And why we would do that is because if we can discard frames from the footage, instead of inferring on or sending every frame to the object detector, we can also then save on inference time. So just making sure we're sending as little frames as possible through the model pipeline is really going to help. And then we can extend our model from human detection to actual testing it on real life footage. So poacher detection on the drone in the park. We were also asked to explore animal detection, but unfortunately, the tight time window didn't allow. So detecting different types of animals, being able to automate the census count process. So the park often needs to do manual census of the animals in the park. So a helicopter will fly and they will be counted using various techniques, but it would be way better if a drone could automate that process. So also being able to predict the animal's gender and age. And then lastly, carcass detection. So detecting where dead rhinos are or dead other animals, so that the rangers can quickly attend to them and maybe still catch some poachers. So thanks very much. If there's any questions.
Usually people take a little bit of time to come up with the questions, so I'm going to take this to kind of give my comments. Really crystal clear presentation, and you know, it sounds like from everything that you sketched here that we could do like a whole separate challenge on just the RGB data, and it's like an amazing foundation for that. So that's really cool. And now I hope maybe already a question appeared in the chat.
I also think it's really nice how you guys came up with solutions to increase the frames per second by just removing a lot of unnecessary data to analyze. So pushing as little through the pipeline as possible. I think that was a very good step.
I think there's a question here from Laurent. Is the color worn by the humans impacting the performance? So I'm guessing that's referring to what they're wearing.
Yeah, so unfortunately we weren't given too many videos where the rangers like tried on different outfits, because I'm assuming they shot all the footage in one day. But I think that obviously if they wore clothing that very well camouflage them, it will add to the challenge. But for now, I wouldn't foresee a massive performance decrease. But again, you'd have to test it.
Can imagine.
Once again, incredible work. Really
Thanks.
congratulations. Love.
All right. If there are no more questions about RGB exploration, I think we can head on to the hardware group and get Noel's question answered. So I'd like to give the floor to the hardware group.
Hi, everyone. I am Kamalan, but everyone calls me Cam, and I will be representing the hardware subgroup. Big shout out to the rest of my team, especially Adrian, Faz, and Mert, Sail. Without your guys' input, we would have never made it this far. Our goals were to run the models that we received from the other teams and implement them on a Jetson board. We had access to nanos and they worked very well. So yes, that was our main thing. And then the other thing was to do handover documentation. So something that would hold your hand if you were to implement this again, which would come in very handy on part 3 of this project. Our approach was to establish a network of nanos. We had a nano in the Netherlands set up in Eindhoven for us that we could SSH onto. Another one in Turkey, which was with Mert. One in the USA, which was with Faz, and one in India that was with Sail. We set up those nanos environments such that they worked well with when they were running models. Then we would receive models, integrate them into the nanos and test them. We also would document what we did and compare the models, and we tried to prepare a framework for future work. So this is a table that Faz found, which came in pretty nice for comparison. So what this shows us is different image computer vision tasks on Jetson boards. And based on our chats with Robbie, the nano works really well, right? We can do people detection and we get about 11 FPS, but it may be worthwhile to consider something a bit more powerful than a nano, especially considering that Spots wants to do other things other than just detection. For example, the animal consensus, because yeah, these things can get hot if you ask too much of them. So yeah, that's something to consider. The basic setup of the nano was that we would like to have the nano set up running the model, and then there's also the Pixhawk, which is mostly dealing with navigation, and we want to have the nano communicating to a computer that's on the ground. Right now, that would be with via the Hearlink 2, and eventually, hopefully, that'll all be backed up to the cloud the next time that laptop has access to the internet. But you never know, maybe with satellites beaming internet down from space soon, maybe we can run this all on the cloud or something. But yeah, we will wait and see. The way we were working with the other teams is we would receive a model, a requirements file. The requirements file shows everything that is required in the environment to run the model. Validation data, a README file, which is something that kind of tries to hold your hand so that you can implement the model, as well as the metrics that they were able to achieve on their powerful machines, so not edge devices. Things like Colab and Rescale. Then from there, we would set up the environment of our nanos such that they could run the model, convert the model. Typically, that was done to, the conversion was done to TensorRT, which is NVIDIA's framework for running machine learning models. It just runs models way more efficiently, specifically for the Jetson platform. And then we would run those models on the nano. Okay, there we go. So I am going to show you guys a video of us running an inference. For some reason, it doesn't want to go to full screen. There we go. Is this presenting okay?
Yes, yeah, we can see the full screen.
Okay, perfect. Cool. So this is the YOLO S version. And there we can see she's picking up a human that's walking on this road thing here. The FPS is nearly 14 frames per second, which is excellent. And the temperature is staying pretty cool. If we look at the bottom right, it's around nearly 40 degrees Celsius at room temperature. We also see a false negative there. I think that's a rock, but yeah, did pretty well on the Nano. Okay, then we'll move on to the V5M. This is the YOLO, and this is the YOLO model. Cool, there we go. Another human being detected, and it's taking close to 6 FPS, as Jaka said. But here we see it's getting a bit warmer, right? Because it's requiring more compute. And yeah, also the GPU is being used to close to 100%. So that is probably the bottleneck. If we want this thing to have a higher FPS, we would need something with a more powerful GPU. Yeah, so the YOLO models were pretty great. We also had VGG net models. And here we see it detected a poacher. So it does work on the when we implement it on the Nano, and they didn't see the poacher. So yeah, that's working pretty well. Yeah, and something interesting about the VGG net model is it ran on the CPU. So it didn't seem like it really needed a GPU that much. But there we see the CPU was actually what was causing the bottleneck in terms of hardware. Everything's in the 80%. And our temperature is around 40, which is not too bad. Okay, unfortunately, there was some, we had some issues setting up the Retina net. We should be able to do it within the next 2 weeks. It's just there's dependencies that's making it take longer than we expected. But the Retina net model is the one that's responsible for working with the RGB data. Okay, and where are we right now? So we can run the YOLO models on the edge. We can also run the VGG net models. These are all models that are responsible for working with the thermal imaging cameras. So those are grayscale images. When we convert those models to TensorRT, the performance increases by about 3 times, which is incredible. TensorRT is the framework by NVIDIA for Jetson boards. So right now, our top competitors is the YOLO V5M and the VGG net. And we have preliminary IO definitions set up. What's in progress is our Retina net for working with the RGB data and doing comparisons on that one there. So lessons learned is on a high level, workflow and collaboration worked very well. Integration and planning could improve. ML ops, unfortunately, we identified the need for ML ops a bit late in the project, but if we identified it earlier, things would have been much easier for everyone. We did have to do a lot of running around to get the stuff we needed. And there's a lot of the small nitty-gritty stuff that was particularly difficult. For the next steps that we'd like to see for the next phase of the project is a mature MLOps pipeline. You know, ideally something where we just commit code and eventually that winds its way onto the drone when the drone is connected to the internet. That would be first prize. To formalize the model performance monitoring, maybe something that runs on the drone and is automated. Because yeah, this the Jetson boards can get hot. Finalizing the toolkits, making it more plug and play for spots. Temperature control, as I said, the Nano can get hot. It is a bit of a concern if we're going to use this thing on game reserves in South Africa, where it's not just room temperature. In the previous project, when we tried running the Detectron 2 model, the major issue there was keeping the Nano cool. So that is something we need to play around. And then dust filtration, you know, if this thing is going to be in the bushes, it's probably going to get very dusty, and these things are not cheap. So yeah, we might want to look at putting some sort of filter where the compute's hardware is stored, where the edge devices are stored. And yes, then we have documentation that will hopefully assist in part 3 of the project. Only RetinaNet is still a work in progress. So yes, that's everything from me.
All right. Are there any questions about the hardware? Noel, was your question answered?
Yeah, thank you so much. Only thing I foresee is the cooling is going to present a challenge, but perhaps we can do something clever by using the drones or propellers to funnel the cooling onto the CPU to help it cool.
That'll be very cool, yeah.
Yeah, Cam, sorry, back to that same, we had this issue before, and all we did is expose the aluminum fins to the air. I mean, we're flying at an average speed of about 40 to 50 Ks an hour. And, you know, if you told me, Rob, there's an optimum temperature to be achieved, I'm sure, you know, 100 meters plus is always a couple of degrees cooler than it is at the bottom. So I'm sure that we'll be able to overcome that from a temperature perspective. And then there was something else you mentioned, was temperature, dust, obviously that is generally enclosed in the console of the UAV. So that shouldn't be a problem. So yeah, I'm hoping that the temperature will be, you know, dealt with by virtually placing it in the plane, and it'll be kept cool with the airstream going over it.
Okay, wonderful. It's good to hear.
Cool.
All right.
If I could maybe just add there, Rob, I'd enjoy for you guys to have a bit more discussion about the potential for using something other than the Nano if we need additional compute power, and what that platform would be. So, you know, with this kind of think tank around us, I mean, let's take advantage of all the knowledge that's out there and see, you know, maybe what the next step is. Nano might be the answer now. But let's see what other opportunities are out there or options are out there.
Yeah, I think using the Nano was something that we stuck on right on the beginning, purely from the fact that right in the beginning, I think from a challenge 1 perspective, the Nano was chosen and we stuck with it. It seemed to do the job just fine. Going forward, if we look into the RGB stuff that Samuel was touching on, I think maybe something a little bit more powerful. But as mentioned right in the beginning, the thermal camera delivers 60 frames per second, and your RGB stuff can be obviously a hell of a lot more. But it's not necessary to send every single frame through. So that may be a way around it. But if we need more compute power, we can go to the next Jetson up from the Nano.
Yeah.
You could also consider having 2 Jetsons.
Oh, there you go.
Robbie, on that note, one is to bear in mind, and that's when things are working very hard, as in computing, and then generating lots of heat, they're going to draw very heavy on batteries. We need to look at just how much battery time we have and how much uptime we want, because that will be the next challenge. Obviously, they're very hungry for power, just into something to bear in mind.
Yeah, look, I said to the guys right from the beginning that the first thing is to get the system working. I would sacrifice half an hour's flight time to get a system that works exceptionally well. But yes, we will look at power consumption was one of the criteria that they should just be wary of. But when I realized that it only, correct me if I'm wrong, Cam, I think it was only 10 watts of power consumption. I don't know what it runs at, if that's at its max, but 10 watts I can live with.
Yeah, for the Nano, yeah.
Yeah. So yeah.
That's even its maximum. Like Nano actually runs on a normal phone charger, so it doesn't require a huge power source.
Okay. Look, that's something we can look at in the, the next challenge. But I think for now, the idea is to get the set working. And like I said, I'm happy to compromise a bit of flight time to get a system that actually works and be less reliant on the human factor.
Yeah, cool. Wonderful,
Okay.
wonderful.
Cam, thanks so much. That's awesome.
Can I ask
Great,
Cam
thanks.
a question?
Sure.
Hey, Cam. How you doing, man? I just wanted to ask you, you mentioned that the one video runs off of the CPU only, if I understand that correctly. Can you not make it run half CPU and half on the GPU? Jeez.
We haven't tried.
Well, is it possible?
Look into.
Is it a possibility?
Yeah, so we haven't looked into that here. So I would be lying if I told you it is possible. That's something we'd have to investigate.
Well, just to add on that, normally if you get like a few FPS on the GPU, like let's say the 6 or 5 that we saw today, there will be like a huge amount more on the CPU. Like it would only do like a half frame per second. So that wouldn't be much of an addition. And then on the other side, the device needs its CPU to actually process the data, because the inference time that they show is only the computation done by the AI. But before the data gets into the AI, the CPU needs to move the image around, maybe do some augmentation provided to the GPU, and then also process the results. Because there's also like the overhead processing needs to be done by the CPU still.
So you're saying it's going to work harder?
Yeah, it's yeah.
Okay. All right. So it wouldn't help the effect.
It wouldn't make much of a difference anyway, and it will probably just make the whole process slower, since the overhead computations will be slower then.
All right.
All right. Since we're already over time, I'd like to head on to the last group because we have some very interesting autonomous flight team who also would like to share their results.
Okay, yeah. Good evening, everybody. Good evening to Spots, Fruit Punch, and whoever else is on the line. My name is Jared Duplessis. I'm representing the autonomous flight and landing team today, and I'll be taking you through the progress that we've made so far. To start with, just introducing our team. We've got Nish, Ryan, Christu, myself, Shai, and Calvin. Luckily a few of us are in sunny South Africa at this point, but I know Nish is, I speak under correction, but I think in the Netherlands. We definitely got the better weather this side, but really nice to be working on a project that's so close to home, and to have so many young South Africans involved is great. A bit of background. This particular aspect of the challenge is brought out of the fact that Spots is still flying their UAV and landing it manually, and this opens up its flank for a lot of damage, and damage in terms of the landing. But on top of that, it increases the skill level required for the operator. So if the end goal is to make these anti-poaching UAVs pervasive and really maximize coverage, you need to decrease the amount of specialist knowledge required to fly, land, manage, all aspects. And of that, we started looking at what is essentially an autonomous landing system. So given that our team didn't really have a super defined problem definition, we went about spending some time on actually making one ourselves. And this was brought out of the fact of speaking to Robbie and a few of the other extra Spots, and really trying to nail down what would give them the best bang for their buck at this stage, and what can our team bring to the table at the early stage of this problem. And yeah, it's kind of distilled into these 4 points that you currently see on screen. Mainly that, yeah, manual landing of the drone requires an operator in the field. Either way, there's going to be an operator in the field, but then point 2 and 3 come into play, and that is you want to minimize the risk to the operator, being that you are operating in what could potentially be a hostile environment, being that there could be poachers nearby. But on top of that, also, if you've got wild animals, it could be the night time. You don't be walking around the bush just for the fun of it. And then minimize the need for skills, and lastly, minimize potential for plane damage. You don't want to be bringing in an unskilled pilot and ask him to land what is a very valuable drone manually, and then take the drone out of operation. The drone itself is particularly hardy. However, you can't fish it out of trees all the time. Maybe if you can see here, it's not Robbie's best landing video, but it's one for context. So we're looking to hopefully move away from that. Okay. So next up, out of that problem definition, we came to a few objectives, and these did mutate during the course of this particular challenge. But by the end of it, I think we've got them pretty defined. And those are, create an autonomous landing simulation to land the drone in. Really bad English, but essentially, we needed to understand the hardware, understand the use case, and develop possible systems and procedures to enable this sort of autonomous landing, or augment what is already there. And we came up with the following bullet points that could, in the future, really aid spotters operation. That is, the drone needs to identify and land in a safe area, which is the runway. Most times it's apparently a road. On top of that, it should be able to take into account or mitigate the effects by localized wind, like wind shear, or bubbles and troughs, minimize operator input, as previously said. And then on top of that, how, as a team, what do we need to propose to enable this sort of use case? So in terms of hardware, procedures, and how do we facilitate that going forward? So we took quite a broad brush at the problem when we started with a bit of research. And I don't want to get anybody's feathers rustled up, but most of the good ideas come from the defense industry. And but that started with what capabilities do we have? So we looked at the hardware. We looked at the onboard flight controllers, the computers, what sort of telemetry we have, the types of GPSs, all the like, and really built an idea of what's on the plane, what's flight proven, and then look at how can we augment it. And the augmenting part, that's where the research came in, and that was, okay, if we want to land this thing at worst case scenario at night on a narrow road with minimal operator input, how do we go about that? And there's a few ways you could do it. You can do terrain mapping, similar to what cruise missiles do. You could do what's essentially heat seeking, or like a Sidewinder missile, like a heat seeking sort of thing, and place down some sort of beacons. And that could be done in the visual spectrum, infrared spectrum, radio spectrum. I see Noel's online here, and he gave us a few really good pointers, especially when we came to some of the stuff we're proposing, and brought us down to earth. So thank you, Noel. And then the last consideration out of this was use case suitability. So of all these grand ideas that we had, what is the most, well, we have a term that's use case suitability. You're flying this in the bush, and it needs to be fit for bush service. And that basically came down to, we need a GPS tracking and approach landing augmentation system, very similar to what is typically known as an ILS, an instrument landing system, which is used in commercial airlines, coupled with what could be an active ground system, but we will get back to that. So research continued. During this course, we were very fortunate to speak to a lot of subject matter experts, namely the guys from Spots, Noel, Daniel from Pixhawk, who unfortunately, I don't think he's in this meeting today, but he gave us a lot of very valuable insights into the inner workings of the flight controller and what potential there is for augmentation and using what is already there and minimizing the reinventing of the wheel. And then lastly, the Pixel community, which Shai was very, very involved with, and yeah, we got a lot out of them, so thank you. Moving on, out of everything, we decided to develop a simulator, something that's real world accurate, that can allow us to do what's essentially software in the loop simulations of particular approach angles, loitering dynamics, and try and fudge in maybe some real world error and see what potentially, like for example, beacon layout geometries would work best given the flight dynamics of the plane. Spots was kind enough to give us access to some of their log files, and from there you can augment the simulator to perform as a real plane does, and see, for example, turning circles and the like. And this provides us an environment to do no risk tuning, so get you as close to a potentially implementable system for as little cost and relatively quickly. So here's a bit of an example that Ryan put together, forms part of our tutorial material, but it's about 34 seconds long, and you can see him going through the thing. So this is us piping pure ROS code into the flight controller, and yeah, we're going to go and try and do a bank right turn. Unfortunately, I don't think he sticks to landing on this one, but it's a great illustration of how versatile the simulator is. On top of the simulator, what you can do is augment the environment and actually overlay what could potentially be sort of video data, infrared data, as we've seen in the previous slides, and then get the simulator to generate, for the lack of a word, new training material. Yeah, I won't speak on that. That's not my area of expertise at all, but it is a possibility. So out of that simulator, we're looking at what's essentially three things: waypoint control, approach altitude, and approach trajectory. And all three of these form the main constituents of sticking an automated landing. The three of these then flows directly into what essentially is the PX4, the flight controller's standardized landing algorithm. And this basically takes a skilled operator, he does a few touchdowns and just records the data, and then that trains a very, very rudimentary model that then executes what's essentially a blind landing. We did look into creating what's more of an active landing system, but at this stage of the project, we surmise that it's more bang for your buck to utilize what is already there and augment it where necessary. So better approach and better altitude control. Approach and altitude, that comes out of our hardware recommendations, one of which I know is going to be done, is putting the LiDAR on, and then on top of that, accurate mapping of the landing sites. So that will be done with an RTK GPS system, the details of which are to be determined. But that seems to be the best, most bush-ready, what do you want to call it? Bush-ready way to go about it. So lastly, maybe some deliverables of what the team has actually accomplished so far. I'd like to say that we did a pretty extensive technology selection investigation. Stems from the problem definition that we put together right at the start. Now, there's a lot of topic research, subject matter expert consultation, scenario-based brainstorming, and use case recommendation and adoption strategies, which are outlined in some of the documents that we put together. We've also put together a Dockerized simulation environment. This was mainly to enable our various team members to work in a standardized environment. And then with that, we, as a part of the course, we put together some documentation, walkthrough videos. Nish and Ryan were instrumental in that, and that brought our team up to speed, and it will definitely help the next teams going forward, or should the challenge progress. And then, yeah, lastly, we got the pipeline got the line ready to pipe cross code straight into the flight controller, and that opens the door for further augmentation of the flight characteristics, be that through a separate computer, whatever it could be. It could be a Jetson Nano, and you can issue custom loiter commands and actually auto loop around a potential target. Moving forward, real world integration, that's probably going to be the next step. We do want to get the stuff off the ground, and there's three main parts. First thing is upgrading of the onboard GPS system. The better you know where you are, the better the rest of the system is. Identification of a suitable RTK GPS system. We've had a look at a few DIY ones. I think I mentioned to Robbie, it might just be easy to buy one. Just need to put our finger on it. And then lastly, simulation testing of more approaches and really getting our procedure down right in the simulated environment. And then lastly, testing. The next best thing would actually be to move away from the software in the loop simulation and actually implement it on hardware and do a hardware in the loop simulation on the ground. And then, upload it and press play and actually see how our little thought experiment works. And then lastly, just saying thanks, Spots, Robbie and the crew. You guys have been instrumental in actually bringing us up to speed, and then you've been very, very open and willing to help in this problem. So I hope we've put together a bit of a framework to move forward. And then, our team, weekends and evenings. Thank you very much. And lastly, Fruit Punch for putting it all together. Thank you.
Thank you so much, Jared.
Those kind words. Thank you, Jared, for all your hard work. It's been a pleasure facilitating everything for you guys.
No, it was all the team. It was very little on my side.
And everyone else, of course. I believe this was the last presentation. Buster, would you like to give some final words?
Do we maybe want to have some questions? I have final words, but maybe questions for Jared or?
Fair point.
They usually start to pop up like it takes 7 seconds
Jared,
to load.
I'll tell you what, I look forward to having you up in the Pilansberg for some white knuckle time. When that air coming in with, a FLIR thermal camera hanging off its butt, and you hit it nail right on the head. I mean, it's white knuckle time trying to land that thing manually, and we stress ourselves sticking every time it happens. So having an automated landing system, I mean, what a pleasure. I think it's too late for me to save hair, but I think it's probably going to save Robbie some. And so just thanks very much for your contribution, and we look forward to seeing it all work. Cool, man. Thank you.
Thank you very much.
Yeah, absolutely. I think there is no question, so then I'll just say my bit. I mean, like this whole last 1.5 hours, I was really at the edge of my seat. Like, this was just such clear presentation and delivery, and it's so incredibly interesting. And maybe some of you might be like, who is this guy? Because I've been more in the background during this challenge. But that tonight allowed me to really get this from the perspective of really looking at your final product, and that's just so incredibly impressive. It's really like it's so amazing for me. Yes, and the reason I've been more in the background is also because I've been focusing more and more on all the other stuff that enables us to do these kinds of challenges and bring them towards implementation. And the only reason that I can do that is because I have Dorian and Sako and so many other amazing people on the Fruit Punch AI team. So thank you all for that, absolutely. And I also want to thank, well, the whole team here for a lot of amazing feedback, because we're constantly, you know, working on really improving the way that we run these challenges. But if I look at the results from this challenge, like I can't imagine what we're going to come up with in as a community in 10 weeks when we put through all the feedback that we've gotten during this challenge. And really, you know, really working on these kinds of challenges, you know, preventing poaching and fighting climate change and all the stuff we do in healthcare, it kind of requires an unrealistic sense of optimism and hope about, you know, the things that we can change in the world. And I say unrealistic because it is against the odds, it is against all odds. And that's like really requires just a special type of person to then still sink your teeth in these kinds of challenges. And that is just like, you have no idea like how special that is, that you're here, that you're working on this. Really, it's like a vast minority. And you know, I hope we can motivate many more people to do this, and like keep educating people to think kind of in this kind of context and use their skills in this way. Because, you know, that's the only way that we're gonna turn this world into something that we might at some day say like, wait, maybe like the whole world isn't on fire. Now, I'm down here in South Africa for the first time after 2 years, when we started with setting up this grander project that has required now 2 challenges, and it's going to require probably a couple more challenges. And what the really cool thing has been about kind of the last few months is that it allowed me, because you're working on this and with this amazing team together to run these challenges with you, it has really allowed me to focus on setting up some bigger partnerships. So I have what I think is a pretty cool announcement to make, and that is that we are setting up an AI for Wildlife lab. So what does a lab mean? It's kind of like maybe bullshit management talk, but what a lab means is basically that, you know, we have a bunch more partners that are going to commit over a longer period to bring this platform into implementation, and also a couple of other projects that we're looking at with other partners over the whole continent of Africa to work on wildlife conservation. And you've already seen one of the main partner in this, and next to, of course, you know, very importantly, the stakeholder spots, which is KPI. You already heard Samuel say something about a labeler, who are most probably also joining in helping us in the labeling efforts. Then we have many other partners actually tagging on: Zambezi, Accelera AI. I just got a confirmation from the Kenya Tiny ML community, which is also really cool. Then Ndaba X, a real lab up in Johannesburg, you know, Cape Town University, Sisonke Biotics. So we have a lot of amazing partners that are joining us to really make this into a sustained effort. And I'm incredibly excited about what that is going to allow us to do over the whole continent of Africa in wildlife conservation. And of course, this also means, you know, that we've talked about this at the end of the previous challenges, or the previous weekly meetups, that kind of what the next step in this challenge is going to be. So so this is to kind of ensure you guys that everything that you worked on now is going to find its place, and we're going to implement it. It's just creeping ever closer towards implementation. So that's all I wanted to say. It's really amazing to you know, view this process. I'm so incredibly grateful of everyone that's here, and yeah, like no other words.
Thanks a lot, Buster.
Be happy.
Very nice final words, and indeed, these keep the Fruit Punch platform. Keep an eye on it to follow all the wildlife lab proceedings. And then the final word I would like to give to Robbie.
All right, so I mean, thank you just doesn't seem to cut it. For me, what this has done is inspiring in many ways because, you know, being out there doing what we do is sometimes difficult, and you sometimes feel you're alone. But this challenge, what it's given me is more motivation and encouragement to know that there's so many other people that share our same views and are prepared to actually do something about it. Because, you know, there's a lot of people and there's a lot of lip service. I mean, governments all around, various other organizations that say they're going to do so many things. But here we are, a community of people that actually give a shit and are actually taking their skill set and actually making a difference. I just want to say, guys, pat yourselves all on the back. Thanks. And no words can describe the way this motivates me to carry on doing what we do. And this is for everybody. Yeah. So, yeah, thanks. That's all I can say.
Thanks a lot, Robbie, for the inspiring words. Then I also like to thank everyone for all their hard work and putting all their free time into these challenges. It's appreciated a lot, and I'm sure everyone knows about that right now. So I believe then we can leave on this final note. Thank you, Robbie, a lot, and I'm already looking forward to the next AI for Wildlife Lab Challenge. And I'd like to thank everyone for being here tonight and for all these awesome presentations. And I wish you all a good night or morning or afternoon, wherever you are.
Thanks again,
a lot.
Guys. Cheers.
Thanks a lot, guys.
Cheers.
Thanks
Hey,
so much.
good evening.